Okay, good morning, everybody. Please make a signal if you can hear me, so I know people can hear me.
Yes, Shamim.
We can hear
Okay,
you.
good. Okay, so let me remind you what we were discussing last time. I want to complete the discussion of the so-called local theory of the search for the optimal lattice packing. So this is a theory from the 19th and early 20th century and associated with the names of Korkin, Zolotarev, and Voronoi. And so here's a picture from the previous lecture. First, a definition. We have this quantity here. Lambda, this is a new notation. So lambda 1 is the shortest vector in the lattice L. We normalize by the co-volume to the power 1 over n. So with this normalization, this quantity doesn't change when you scale the lattice by a constant, because if you multiply by a constant, the numerator and the denominator grow by the same amount. The big problem in the field is to find the lattice for which this quantity is as large as possible. We saw last time that such a maximum exists. And so this corresponds to an optimal lattice packing if you can maximize this quantity. And the local theory is talking about, instead of looking for the global maximum for this quantity, you look at local maxima, local in the sense of the topology that we introduced last time, the Chabot-Feld metric. So you want to call a lattice L0 critical if this function achieves a local maximum in the usual sense. It means there's a neighborhood of it where the every point in the neighborhood, the value of the function is no higher than it is at this point. Then it's a local maximum, and we call it critical, and we're trying to find the critical lattices. So that's what we were discussing. And there's a basic geometric intuition, and then this basic geometric intuition gets transformed into some problems in symmetric matrices and linear algebra. So here's the intuition. You want to define so these purple dots are the vectors of a lattice. In this case, it's a picture of Z2. And they're the ones that I've just marked, these 4 points, are the shortest ones. And if you can, uh, saying that you can locally increase this function by changing the lattice is the same as saying that you can fix the lattice and change this Euclidean ball, which is the Euclidean ball whose radius is the length of the shortest vector, to an ellipsoid of bigger volume. And why are those two problems the same? If you can find in the same lattice an ellipsoid like this, which only touches lattice points on its boundary, and it has larger volume, then there's a linear transformation that maps the Euclidean ball to the ellipsoid. And if you apply the inverse of this mapping to the lattice will change to a new lattice very close to the old lattice because the ellipsoid is close to the Euclidean ball. And since the ellipsoid has larger volume, the new lattice will have vectors outside the pre-image of this ellipsoid, which is a bigger ball. So that would give us an indication that this lattice is not critical. Okay, so is this basic intuition clear? So perturbing the lattice locally and looking for the length of the shortest vector in the new lattice is the same as perturbing the Euclidean ball locally, or perturbing the Euclidean norm, if you prefer, locally into an ellipsoid, and looking for a new ellipsoid which is close to the original one, whose volume is larger and does not contain lattice points in its interior. That's the basic observation behind this whole theory. And it leads us to a discussion of symmetric matrices and linear transformations on the space of symmetric matrices. Please stop me if you don't understand this intuition. because this is kind of the basis of the whole thing. Okay, so I'm going to remind you of some definitions and notations from the previous lecture. So everything here sort of, I'll try to remind you of what happened in the previous lecture, but it's all very much dependent on things that we already did. So here's our notation. Sim n are symmetric n by n matrices. We had a mapping that mapped a matrix G into G of GLNR into this symmetric matrix, G transpose G minus the identity. We call this mapping A, so G maps to A of G. It maps the identity to the zero matrix. It's open in a neighborhood of the identity, which means the following thing. There's a neighborhood of the identity in GLNR such that the image of this neighborhood under the mapping A is an open neighborhood of zero in symmetric matrices. And if you take any smaller neighborhood, U0 of identity in GLNR, you map it under this mapping, you get a smaller open neighborhood of zero in the space of symmetric matrices. So a small local change in G, which is going to transform the lattice to a nearby lattice. We'll take a lattice G and apply. We'll take our lattice L, I'm sorry, and apply this small G to it, transforming into a nearby lattice. That locally, in the language of symmetric matrices, corresponds to changing zero to this small symmetric matrix. And this is the change, the infinitesimal change in the Euclidean norm, or in the shape of the ellipsoid, because when you have a symmetric matrix, you can form a definite, sorry, symmetric matrix close to the identity, then you get a positive definite bilinear form, which gives you a norm close to the Euclidean norm, and therefore an ellipsoid close to the Euclidean ball. Okay, so I hope the intuition is clear. So we had a little computation that I want to recall. What's the fiber of this mapping? In other words, when do 2 points, 2 matrices um, map to the same symmetric matrix? So this is something that I said I didn't do the computation completely. Two, G1 and G2 are mapped under A to the same symmetric matrix if and only if G2 differs from G1 by left multiplication by an orthogonal transformation. So let's go over this computation. So A of G1 equals A of G2. If and only if this happens, this is a definition of the map A. moving this over to the other side, I get that the identity is the right-hand side times the inverse of the left-hand side. So this is this quantity. I can conjugate this quantity by the inverse the inverse of G2, and that has the, or in other words, this identity says that G2 transpose is the inverse of this product, G2, G1 inverse G1 minus inverse transpose. So I can move this guy to the other side because this matrix and this matrix are inverses. So if I move it to the other side, I still get this identity. And this means that this term, G2, G1 inverse, is its own, its inverse is its transpose. And so that means the G2, G1 inverse is an orthogonal matrix, which means this. All right. So that's something that I said last time, but I didn't do the computation. We're going to see some of these computations again. So I thought I'd make it clear, spell it out. Another notation from last time is the following linear functional on the space of symmetric matrices. You given a vector in Rn and a symmetric matrix A, you can look at this inner product. It's basically the norm squared of X under the norm that is associated with the symmetric matrix A. And as a function of A with X fixed, it's a linear function. So this is a linear functional on the space of symmetric matrices. It will play a big role. The minimizing set, or the set of shortest vectors of a lattice L, are the set of vectors which realize its value of lambda 1. So these are the shortest non-zero vectors of L. And we say that L is perfect if the corresponding linear functionals that you get from this formula span the dual of the symmetric matrices. So this was the definition of perfect, and using this definition, we prove the first theorem in this chain of results, and it says that for a critical lattice has to be perfect. So it has to have lots of shortest vectors, sufficiently many, so that these linear functionals span the dual of the space of symmetric matrices. And we proved this last time using two lemmas, one of which I didn't have time to prove and one of which I did. So let me recall those two lemmas. So the first lemma is lemma 2. It was lemma 2 last time. And it says the following. So for any lattice, there are neighborhoods of identity in GL and R and of 0 in the space of symmetric matrices, so that if you're close to identity and you want to know the shortest length of the shortest vector of the image of L under G, where G is in this small neighborhood, this quantity, and you square it, you have the original length of the shortest vector plus the minimum of these linear functionals. Um, um, these linear functionals on the matrix A, which is the image of G under the mapping that we had. Okay, so this is a lemma that expresses the new value of the shortest vector in the lattice in terms of the old one and in terms of these linear functionals. And the second lemma is about the determinant function, and it says the following thing. There's a neighborhood of 0 in the space of symmetric matrices, such that for any element in this neighborhood that has trace less than or equal to 0, two things may happen. Either the matrix comes from an orthogonal transformation, or its determinant is strictly less than 1. Okay, why? So these lemmas are discussing two different functions. One of them is lambda 1, the shortest vector in a lattice. The second is the determinant. Let me remind you that the function that we care about is this function, which is the quotient of these two things. And we are not working with lattices of covolume 1. It's convenient in the proof to allow covolume to change. And so we care both about the numerator and the denominator. And so lemma 2 is about how this function changes locally, and lemma 3 is about the determinant, which dictates how the denominator changes locally. So that's lemma 2 and lemma 3. I proved lemma 2 last time, but I didn't prove lemma 3, so now I'm going to prove lemma 3. Okay? So let's prove lemma 3. So so let's start with so one more, another thing to say maybe about lemma 3 is that basically you're going to see the main point here is that the trace of a matrix is in some sense the derivative of the determinant. So there's a relationship between two kind of classical functions on matrices. One is a trace and the other is a determinant. If you think about the matrix A as being like a linear approximation, like a first derivative, a directional derivative in the space of matrices, and you think about differentiating the determinant function in this direction, like a directional derivative, then the main term that pops up, the linear term that pops up, is the trace. So that's the main point of this lemma. So let's start with a matrix of trace non-positive, non-zero, and which is an image of some matrix G under our mapping. And um, for now I'm taking the U, which appeared in the where did this go? Which appeared here. So this is the U along which this mapping is an open mapping. I'll make U smaller in a moment. And let's define the following function. Let's call it H from the interval 0, 1 to real numbers. H of S is the log of the determinant. So I'm taking A and I'm thinking about it as a first order. It's giving me a one parameter family of matrices varying linearly, starting at the identity, and I'm taking their determinant and taking the log. And let's let lambda 1 up to lambda n be the eigenvalues of A. So maybe this was a bad choice in notation. You shouldn't confuse this lambda 1 with the previous lambda 1. It's just an eigenvalue. And so A is symmetric, so it has real eigenvalues. And the determinant of the identity plus S of A is the product of the eigenvalues of the identity plus of S of A, which are lambda I plus 1. Right? A has, sorry, there should be an S here. Right? A has eigenvalues lambda 1 up to lambda n. SA has eigenvalues S lambda 1 up to S lambda n, and I'm adding the identities. So these are the eigenvalues of this matrix. Then I take the determinant, then I take the log. So this is my function h of s. Let's differentiate it. So h prime of s is this. And let's differentiate it again. And we get this. Okay. And let's evaluate these derivatives at 0. So I plug in s equals 0, and I get, for the first derivative, I get the trace of A, which we know is non-negative, non-positive. And for the second derivative, we get minus lambda I squared, which is strictly negative. So what you're seeing is there are two cases. If the derivative is never positive. If it's negative, then this means that h is decreasing close to 0. And if the derivative is 0, the second derivative is strictly negative. And again, the function is decreasing near 0. So in both cases, this is a decreasing function near 0. So for s in some small neighborhood of 0, one-sided neighborhood of 0. So let's call this S between 0 and let's say R depending on A. Um, h of s is strictly negative, which means that the determinant is less than 1, which is what we wanted almost precisely. We wanted to say that there's a small neighborhood in which the determinant of g is less 1. So that what's the relation between the determinant of g and the determinant of the identity plus SA? This is the determinant of, so the identity plus SA is g times g transpose. And so this is the determinant. Okay, so we got the conclusion that we wanted in the sense that we got the determinant to be strictly less than 1, but the neighborhood that we had was a one-sided, was a an interval which depended on, whose length depended on a. And this is not exactly the way the lemma is stated. And so now there's a something which I'm omitting, which is a, like there's a compactness argument, which I leave for you to check. We can choose this neighborhood RA independent of A to get a neighborhood V of 0 in symmetric matrices such that um, we get this. Okay, with a trace none. So that's a proof of lemma 3 module. Yeah.
When you do just on the top of your tablet now, you have to extend this to s equals 0, right? Or am I missing something?
Oh, I'm sorry. This is
because you're using it at 0. Or
maybe. No, I'm not using it at 0. I'm using it at A. Right. So A
no,
of
I mean
S equals SA. So I'm sorry. So the definition of A, where does this go? A is A of G. Okay. Which means, where is our definition? Which is this, right? So identity plus A is G transpose G. I'm not using it at S equals 0. I'm using it at S equals 1. And what I should have said is, I don't want to use it at S equals 1. I want to use it at small positive values of S. And so I'll use it, I'll make a new notation. S times A is not 0. It's S is a small positive number. So this is a small matrix. And the mapping, I can find a preimage of SA, and I'm going to call it GS. Okay. And then this just equals that. Okay. So this GS is in a small neighborhood of 0 in G, of the identity in G, and we get the conclusion for it in the small neighborhood. Is it clear now?
Yeah. S equals 0 would be useless anyway. That's correct.
Yeah. All right. So that's the proof of this lemma. And so you saw in the proof of the lemma, again, what I said verbally, you saw that the relationship between the determinant and the trace. The trace right here, you see that the trace is, this function is the log of the determinant, and its derivative is the trace. Okay, so now I want to understand what happens when this condition that the trace is negative is no longer valid. And so I need another definition. So a cone in a vector space R to the n is a set C, which is it's convex, but it's a stronger assumption than being convex. If you take any 2 points in this set and any 2 real numbers which are non-negative, and you form the linear combination with these non-negative coefficients, you get an element of your cone. Okay, so if we were using the definition of a convex set, we'd only take alpha and beta non-negative with sum equals to 1. So that would, so pictorially, if this is x and this is y, in the definition of convexity, we're requiring the line between them to be in our set. If in the definition of a cone, if this is 0, we're requiring all of this to be inside our set C. So that's the definition of a cone. And so I'll just write it here. So in particular, a cone is convex and closed under multiplication by non-negative scalars. And the lemma we want is the following thing. We take a closed cone, and we want every element in this cone, which is not 0, to have positive trace. Then there's a neighborhood V of 0 in symmetric matrices such that for all matrices in this neighborhood and inside this cone, which are non-zero, the determinant is strictly bigger than 1. So let's just compare. The proof is similar, but let's first compare this lemma to the previous lemma. In the previous lemma, we cared about negative trace, and we got that the determinant is strictly less than 1. But it's not just negative trace here. We also allow trace equals 0. And when we allow trace equals 0, we run into the analysis of the second derivative of this function. And the second derivative tells us that the determinant that we care about is strictly less than 1. Here, we're talking about, there's some noise. Somebody's got some. I'm going to mute someone. So here, we care about the opposite case when the trace is positive, and we want if we want the determinant to be strictly positive, we want to stay away from the space where the determinant, strictly bigger than 1. We want to stay away from the locus where the determinant is equal to 1. We want this to be a strict inequality. Then we should stay in some cone which is closed and satisfies this property. So maybe just graphically again, there's like, this is the origin, this is maybe trace positive, this is trace negative. And if we care about where the determinant is, here we have the determinant of G strictly less than 1, including the boundary, including the line where the trace is 0. And if we stick in a cone, this is our cone C, then here we're going to have trace determinant of G strictly bigger than 1. The locus where the determinant is actually equal to 1 in this picture will be kind of tangent to the linear line trace A equals 0, but it won't be a line. It'll be a kind of a, it'll be curved. Okay, so this is the lemma. And the proof is similar. So I'm sticking a 1 on top to indicate the sphere. So these are the symmetric matrices of norm 1 for it doesn't really matter which norm we choose for some norm. Let's take an element of this, oops, of the intersection of this cone with this sphere, and h of s as before. Sorry. Since the trace is positive, the determinant at 0 of this function h is positive, right? The determinant of this function h is the trace. We computed that. So now the determinant of this auxiliary function is positive. Therefore, as in the previous discussion, there's a number which I want to call R of A, such that for S in the interval from 0 to R of A is some positive number depending on A. H of S is positive. And again, there's a compactness argument that I'm deleting. By a compactness argument, can take R of A independent of A as long as A belongs to this closed cone. Oops, something just happened to my. As long as A belongs to this closed cone and intersected with this unit ball, this is a compact space. Here I use the fact that the cone is closed. I can take RA to be positive and independent of A and use that to conclude the proof. So let's call this sorry. There's a positive R, can take. There's a positive R which is less than any of these R's, and I'm just taking V to be SA, where S is between 0 and R, and A is here. So this V satisfies the conclusion. Okay, so that's the proof of lemma 4. Now using lemma 2, 3, and 4, all these lemmas that we've proved, I'm going to state a theorem, which we're going to need. So basically, we've now completed, once we completed the proof of lemma 3, we completed the proof of this theorem, which I'm calling theorem 0, this Corkin-Zolotarev theorem. But now I would like to get a better description of all these L0s, which are critical. And I'm going to do that with using these three lemmas, 2, 3, and 4. So to state it, let me make another definition here.
Can you
So
pause for questions for a minute?
sure.
I'm a bit confused with the notation. A is a matrix which we achieve by the function, or it can be any symmetric function.
So what I kept sort of doing over and over again, which might have been confusing, is whenever I talk about neighborhoods, I'm always giving neighborhoods the same names. Curly V are neighborhoods of 0, and curly U's, which I wrote over here, curly U's are neighborhood of the identity in G. And I keep using the same letter over and over again, but they're not always the same neighborhood. But I always take my neighborhoods in the space of symmetric matrices to be subsets of this neighborhood. Okay, so the one that appears in this statement. So every matrix, symmetric matrix in this neighborhood, I can think of as an image of this function A. It's in the domain of, it's in the image of this map A. Okay, it's an image of this map A on the set U where the map A is an open mapping. So I'm using this over and over again to talk about these neighborhoods.
Okay.
Does that make it clear?
Yes.
And in different statements, these neighborhoods could be smaller than the one I had before, but not bigger. Okay, so let's say when two lattices are similar, so L prime are called similar if there exists a real number, non-zero, and an orthogonal matrix. So this is the group of orthogonal n-line matrices. Such that L prime is T times O times L. So L prime is obtained from L by rotating it by an orthogonal matrix and then scaling it by a non-zero real number. And so with this terminology, the following are equivalent. Oops. L is critical, which is the property that we care about. And now I want to give a condition about the minimal vectors of L. So if A is a symmetric matrix and the trace of A is zero, is non-negative, non-positive, and the minimum for X, for the minimal vectors of X of these linear functionals evaluated on A is not negative, then A equals 0. So the only possible matrix with these properties, symmetric, trace, non-positive, and these minimizers, achieving non-negative values is the 0 matrix. And C there's a neighborhood U of the identity in GLNR such that for all G and U, either um, okay, so let's compare these three statements, see if I can fit them into, yeah. So First of all, let's ignore the statement B, which is the one involving the object that we're considering, and just compare A and C. A is about L being critical, which means that this function here achieves a local maximum at L, which means that there's a neighborhood of L in which this, the value, so to say that L is critical is to say that there's a neighborhood U of L where you have strict inequality. So, sorry, where you have non-strict inequality. And now I'm claiming that we have strict inequality unless the two lattices in this neighborhood are similar. So it should be clear to you that C is stronger than A. Okay, in C, we don't only say that there's a neighborhood in which L is the largest element, we say that it's the unique largest element up to this equivalence relation of similarity. It should be clear also that similarity preserves, maybe I should have said that, similarity preserves the function lambda1 bar that we're interested in. It's the scaling doesn't affect lambda1 bar, as I noted, and orthogonal transformations don't change the lengths of shortest vectors. So if two lattices are similar, they take the same value of this function lambda1 bar, and if they're not, and we're in a small neighborhood of L, then we have strict inequality. So C should be clear to you that C is strictly stronger than A. Okay, and B is this intermediate statement that involves this quantity, which came up in lemma 2. This quantity measures how the length of the shortest vector changes, and this quantity, which came up in lemmas 3 and 4, which measures how the determinant changes. Okay, and so now I'm going to prove this. It's just putting together these lemmas. So let's prove it. So proof. So as I said, C implies A is obvious. A implies B. Let's prove this by contradiction. Suppose we had a non-zero element of the space of symmetric matrices where this happens and this happens. So this is precisely the negation of B. There does exist a non-zero A such that this happens and this happens. If I multiply A by a small positive number, I can make S times A as close to 0 as I want. So we can assume that the conclusions of lemmas 2 and 3 apply to A. So in other words, I'm replacing A by SA for some small s. It still satisfies these properties. I haven't changed the sign. These are linear functions, so I haven't changed the sign of the trace or the sign of these numbers. And now it also satisfies the conclusions of lemmas 2 and 3, and I call it A once again, even though it's maybe a smaller, closer to 0. And so
so you do
by
not
A, so I can replace it, but I tell you that I can replace it.
No, my question.
Yeah.
Lemma 2 does not really have anything to do with this, or are you already
Uh,
using the existence of some G, or?
both lemma 2 and lemma 3 are about neighborhoods of the identity. Okay, so I want to use these lemmas, and so I want to make, yeah. So the A I will the mapping G maps to A of G is surjective. So for every
So
A there is a G. So I kind of all the time I'm switching between working with A's and working with G's. Okay, but I'm saying that if I
that you
multiply
line
A,
this, yeah.
if I make A small enough, I can assume that any such A, that the A that I get is in this neighborhood V that appears here, and also in this neighborhood V that appears here.
Okay.
Okay. Okay. So since L is the local max for the function lambda 1 bar, lambda 1 bar G of L is less than or equal to lambda 1 bar of L for G such that A of G is A. Okay. Now by lemma 2, lambda 1 of G of L, let me write everything down and then I'll refer you back to lemma 2. Lambda 1 of G of L is greater than or equal to lambda 1 of G, and by lemma 3, the determinant of G is less than 1, and so lambda 1 bar of GL, which is okay, so I'll show you what I did and then refer you back to the lemmas. So first let's look at the punchline here. So lambda, on the one hand, because this is a local max, we have this inequality. But on the other hand, we make a calculation and we get the opposite inequality. So that gives us our contradiction. So lambda 1 bar of GL is bigger than lambda 1 bar of L. Why is this true? Well, this is the definition of lambda 1 bar. It's lambda 1 suitably normalized by the co-volume to the power 1 over n. Lambda 1 of GL is greater than or equal to lambda 1 of L by lemma 2. What does lemma 2 say? This is, we're taking lambda 1 L squared and we're adding something non-negative to it and taking the square root. So that can only increase it. And lemma 3 says that if a trace is negative, the determinant has to go down. And so this comes from lemma 2 and this comes from lemma 1. And when I move from here to here, I've used this. And the co-volume of a lattice changes by the determinant, the co-volume to the power 1 over n, changes by the determinant to the power 1 over n. This number is strictly smaller than 1, so this number is strictly bigger than 1. So I get the inequality that I want. Okay, so that's the proof of the implication A implies B. Let's do the implication B implies C. So I'm going to use lemma 4. For lemma 4, I need a closed cone. My cone is the following. So it's the symmetric matrices for which these linear functionals are non-negative. Note that all of these are non-strict inequalities, so they define a closed set. and all of these are linear functionals. So this is we're doing a we're setting linear functionals greater than or equal to 0, and that's preserved under linear combinations with non-negative coefficients. So C is a closed cone, and then by lemma 4, the trace of A is positive for A and C, and A not equal to 0. What does lemma 4 say? I'm sorry. No, sorry. Lemma 4, this is a hypothesis. Why did I say that? Why did I say that this? I'm sorry, by lemma 4 and by assumption B. Okay, what is our assumption? Let's look at assumption B. So assumption B says that we can't be in the cone that I defined and have non-negative trace, non-positive trace, unless A is 0. So taking assumption B exactly means that the trace of A is positive for A and C, and we can apply lemma 4. So this was somewhat confusing. Let me rewrite this. By 4, by B, we have this, and so we can apply lemma 4. So now let's take U to be the neighborhood, as in lemma 4, and let G and U, and suppose that the determinant of G is 1, and G is not orthogonal. Um, then by lemma 4, G is not in C. I'll show that in a moment. And so what we get, so I'll just conclude the proof, and then we'll go back to seeing why this is true. So then I'll do the similar computation to what I did before. Lambda 1 bar of G of L squared equals lambda 1 of L squared plus this minimum. Okay, so let's review this computation and then go back to lemma 4. So this equals this. That's exactly lemma 2. Sorry, this lambda 1 bar is lambda 1 squared. Lambda 1 bar squared is lambda 1 squared divided by the co-volume to the power 2 over n. And lambda 1, maybe I'll stick in this extra line. So okay, this quantity is this quantity just by definition. This quantity is this quantity. That's lemma 2. And I just copied this quantity. Here, I changed this covolume of GL to the covolume of L, and that's because the determinant, I chose the determinant of G to be 1. Here we have strict inequality because this what happened to my pointer? Here we have strict inequality because A of G is not in our cone. So sorry, this should have been A of G. I'm sorry. So A of G is not in our cone, and so this quantity is strictly negative. The definition of the cone is here. If we're not in the cone, then this minimum becomes strictly negative, and so we get a strict inequality here. This is because A of G is not in the cone, and this is the definition of lambda 1 bar. And so the only thing I need to justify again is why is A of G not in the cone? So let's look at lemma 4. We have the determinant of G equals to 1. And lemma 4 says, where's lemma 4? If we were in the cone, the determinant of G squared, which is the determinant of this number, would have to be bigger than 1, but we know that it's 1. Okay? And so this proves the conclusion that I wanted under the assumption that the determinant of G is 1. If the determinant of G is not 1, then I can rescale G by multiplying by a scalar. This does not affect lambda 1 of GL or the conclusion that we want. Okay, so all of this together proves the theorem. Okay, so we've proved this theorem. Let me leave it up here so you can look at it during the break. So this is giving us a necessary and sufficient condition for being critical, and we're going to work with this after the break. Any questions before we take 10 minutes? Okay, so let's take 10 minutes and continue. Okay, I want to continue. Can people hear me? Just want to be sure that I can be heard.
Okay.
Okay, toda. Okay, let's continue. So in this theorem that you're still, am I sharing the screen? Yeah, I'm sharing the screen, right? So this theorem that you're seeing on your screen is necessary and sufficient for being critical, but we want to have something that we can, more geometric, that we can apply in practice and use. And for that, we need the following geometric notion of when a lattice is eutactic. So definition, a finite subset F in Rn, well, some subset, not necessarily finite, is called eutactic. Yeah, sorry, finite. So a finite subset of Rn is called eutactic if there exist positive coefficients lambda x for every x in F, such that for each symmetric matrix, its trace is equal to the sum over the elements of F with these coefficients lambda x of the linear functionals phi x of A that we had before. Okay, so this is the definition of a matrix being eutactic. Let me, I'm just stressing the fact that the coefficients are positive. It's not, usually when I put a line under something, that means I'm defining it now. I'm assuming you know what I mean by a positive number, but I'm just stressing the fact that these coefficients should all be positive. And so let's compare this to the notion of perfect that we had before. Trace is one of the possible linear functionals on symmetric matrices. So if F is extreme, is perfect, then there exist these coefficients. Sorry. So remember, being perfect meant that these linear functionals span the dual of symmetric matrices. So you can express any linear functional as a linear combination of these particular linear functionals. That's the definition of perfect. And the definition of eutactic seems similar. We just want to express one of the functionals, trace of A, but we want to do so with positive coefficients. And in the definition of perfect, we're not assured that these coefficients are positive. We only are assured that they exist. And so I'm just stressing that. So for eutactic, we need the lambda x to be positive. Okay? And definition, L is called eutactic if the set of minimal length vectors for L is eutactic. Okay, let's just do a quick example, which continues an example that we did last time. Let's take dimension 2, the lattice being Z2, so the vectors of minimal length are plus minus E1 plus minus E2, where E1 and E2 are the first and second basis, standard basis vectors. And so last time we computed the linear functionals phi of E1. Symmetric matrix looks like this in 2 by 2. It's A, B, and C with B on the off diagonal. We made a computation. It's a very easy computation. And we saw that phi of E1 is A, phi of minus E1 and phi of E1 are exactly the same because if you multiply a vector by -1, I mean, in terms of the vector, this quantity is a quadratic form. So you multiply it by -1, it doesn't change anything. And we also computed the same the value of phi E2, and we got C. And so trace of A, which is A plus C, is we can express the trace as the sum of these 4 linear functionals. with positive coefficients, all the coefficients are 1/2. And again, let me stress that if I could also write, let me write it here, could also write trace as phi1 plus phi2, but this would not show that L is eutactic, right? I mean, for L to be eutactic, this whole set of minimal vectors should be eutactic. For the whole set of minimal vectors to be eutactic, I really need to use all the elements in it with positive coefficients. And so this is only using 2 out of the 4 minimal vectors. And so it doesn't, this is a true identity, but it doesn't show that L is eutactic. Whereas here, I used all 4 of them with coefficients 1/2, and I see that L is eutactic. Okay, so this is the notion of a eutactic lattice. And
Sorry.
yeah.
Can you quickly remind me? Sorry, the lattice is perfect, or a set is perfect if the functionals span the dual of the symmetric matrices. Is
exactly.
That okay?
Exactly. So that's why.
So it's neither stronger nor weaker than perfect and eutactic.
Right. So
Because
there's no
this guy
log.
is not.
There's no obvious.
Yeah.
There's no obvious relationship between being eutactic and being perfect.
Okay.
There was a time in history in the 50s where it was an open problem to see whether there are actual lattices which are eutactic but not perfect. And then examples were found. Okay, so it's quite easy to, we already saw last time that Z2 is not perfect. You see it in this computation. Z2 is not perfect because the you're getting 2 out of 3 possible. You need at least 3 linear functionals to span the dual of this space. This space is 3-dimensional. So clearly Z2 is not perfect as we saw last time, but it is eutactic. There are examples of lattices which are eutactic but not perfect. Okay. And the theorem that is a classical theorem of Voronoi, which I'm calling theorem 2, is that L is critical if and only if L is perfect and eutactic. So this is, in my view, this is really a beautiful theorem. I mean, we'll hear a little bit more about the history of this theorem, but this was really a really nice effort to try to solve the problem of lattice packings by understanding the critical lattices, and this gives you a complete characterization. So geometrically, this is basically, it's an if and only if condition. So it's, you know, very, very promising, and we'll see where that led in terms of looking for the optimal lattice packing after we're done with the proof. So this was Voronoj's theorem, and we're in a position to prove it. There are 2 directions here. One is we can already do completely, and for the second, we'll need an extra lemma. So let's prove the direction going this way. So in other words, let's assume that the lattice is perfect and eutactic, and prove that it's critical. So we assume L is perfect and eutactic, and check condition B of theorem 1. Theorem 1 was the theorem that we had before the break, which gives us necessary and sufficient conditions for this theorem here, which gives us necessary and sufficient conditions for being critical. And we want to check condition B, which says that any symmetric matrix with non-negative trace for which this quantity vanishes has to be the 0 matrix. And we're assuming that L is perfect and eutactic. So let's do that. So let's let lambda x be the positive coefficients as in the definition of eutactic. So lambda x is positive for all x, and the sum lambda x phi of x is trace. That's what you get from being eutactic. Let A be a symmetric matrix, and let's assume those conditions. So what B says is we have to take such an A which satisfies these two conditions, and we have to show that it's 0. So we plug it into the formula for the trace. We plug it into this formula here, and we see that the trace is non-positive. That's our assumption. And at the same time, this is the sum. This is this because of this identity. And all of these numbers are positive, and all of these numbers are non-negative because of this condition. And so that implies, so this is greater than or equal to 0. So this implies, so, or let's just put it, yeah, so this, and phi x of A is 0 for all x in min L. Right? If we had positivity even for one value of x, then the contribution in this sum would have been strictly positive, because again, these coefficients are all strictly positive. If one of these were positive, we'd get a contradiction. So now we know that all of these numbers are 0, but since L is perfect, and these linear functionals here span all linear functionals on the symmetric space, we have that phi of A is 0 for all linear functionals on the space of symmetric matrices, and so A is 0. So that verifies the condition B from the previous theorem, and that proves one direction of our theorem. For the converse, we're going to need another lemma. And this is kind of a standard thing in something called linear programming. So I'm not assuming any of you know what linear programming is. I don't know too much about it, but let's state it and discuss it before proving it. So I'm going to call this lemma 5. So let V be a vector space over R, and let V star be its dual. Let phi1 up to phi r be linear functionals on V, then the following two conditions are equivalent. Let me not use A and B, because I have in the theorem, let me use 1 and 2. So if you know that all of these these are conditions about the linear functionals. If you know that for some x in V, that its value in all of these linear functionals is non-negative, then in fact it has to be negative. Then it's non-negative, then it has to actually be 0. For any x in V. That's a condition on these linear functionals. And the claim is that this is equivalent to having positive coefficients such that the sum of the phi's with these coefficients is the zero linear functional. Okay, so this is in the definition of eutactic. We have something involving a positive linear combination of the phi's of certain linear functionals, and we're going to be using this too, but in order to check two, one is going to be useful, and so this is what we're going to need. Let me just say, you'll see the proof. The proof is, there's kind of a repeated induction, which is, I don't know, it's not too difficult, but it's a little slightly involved. Let me just say that if you only wanted zero to, if you only assumed that zero was in the interior of these linear functionals, the interior of the convex hull of these linear functionals. So this is a slightly different version of 2. It's a variant of 2. Then this would be easy. This would be obvious. And that's kind of a completely standard fact. Here we want a not completely standard fact, which is that we want all of these coefficients to be positive. Again, I keep stressing that it's sort of crucial in the use of this condition that all the coefficients are positive. So this is also not very difficult, but it's not the if some of you are used to these kinds of arguments, this is not exactly the standard condition that people impose, I think. Okay, so this is the lemma. And one of the directions is trivial, but that's not the direction that we care about. So 2 implies 1 is easy. And so I'll leave it as an exercise. And actually, we're not going to need that direction. We're going to need the other direction. So let's prove that 1 implies 2. So again, we're assuming that this implication holds for every x, and we want to do this. And let's make a reduction first. I didn't assume here that V is a finite dimensional vector space, but I did assume that the phi's are finite. So I want to now pass to a finite dimensional vector space. Actually, all the action in this condition and also in this condition is taking place on a smaller vector space, which is the quotient of V by the vectors which are the joint kernel of all of these mappings. So if you have an X such that all of the phi's vanish on X, it certainly doesn't affect the truth or falsity of this implication. And it also doesn't affect the truth or falsity of this implication, because both sides would be correct for it no matter what the coefficients are. And so I want to reduce to that finite dimensional vector space. So let W be the intersection of the kernels of the phi's. So phi, so phi induces a linear functional on V over W for any I. Right, phi is a linear mapping on V. It vanishes on W, and so it makes sense on the quotient space V mod W. And so we can just pass to, so the validity of both 1 and 2 only depends on whether they are valid on this quotient. So we can replace V by V wedge V quotient by W, or in other words, we can assume that that the intersection of these kernels is the trivial space, and therefore V is finite dimensional. And now we're going to do an induction on R. So we will prove the implication that we want, which is 2 implies 1. Sorry, which is 1 implies 2. By induction on R and on the dimension of V. In other words, we'll be proving it by induction on R, and for each fixed value of R, we'll be proving it by induction on V. So the base of this induction, so this is the statement is trivial if R equals 0 or the dimension, or R is bigger than 1 and the dimension of V is 0. And
just to be sure,
yeah,
the assumption without loss of generality implies that R is at least the dimension of V.
right,
Correct? Good.
right.
Yeah.
R generates, not, once you have this fact,
You generate the dual.
R generates the dual.
Yeah, good. Sorry,
the phi's generate the dual. Okay, so we're proving it by induction, and these are the two base. Again, it's an induction on R, and for each R we may use induction on the dimension. So these are the base cases of the induction. Let's define a integer m to be the largest possible. For which there are phi I1 up to phi IM distinct, such that the conclusion that we want fails for these this m tuple. So such that such that the implication 1 implies 2 fails for this m tuple, which means that there exists an element of V with all the phi, all of these elements non-negative on it, and not all 0. So, sorry, I didn't mean the implication. I meant that one fails, not the implication. Sorry. So this is 1. To say that 1 is false means that I can find an x so that all of these are non-zero, but all these are non-negative, and at least one of them is positive. So that's what I'm assuming about the collection phi I1 up to phi IM. And I know, since I've assumed 1, I know that M is strictly smaller than R. So this, because I'm assuming now that 1 does hold for this collection. So the largest possible collection for which it doesn't hold is strictly smaller. Since we assumed this assumption 1 for phi 1 up to phi M, sorry, phi 1 up to phi R, we have that M is strictly less than R, and by reindexing, let's just write phi I1, phi M equals phi1 up to phi M, just to make the notation easier. Claim the phi i's from phi1 to phi M span the dual space. And this is by induction. If this were not true, then there's an element in the joint kernel of the phi i's, which is non-zero. And there's some index k bigger than M with right. So if the phi i's did not span the dual, then we could find an element y which was in their joint kernel but was not zero. So this should be a period here. Since we know that if I intersect the kernels of phi i's for all the i's from 1 all the way up to R, I get 0, there exists some phi k, which is bigger than M, such that phi k of y is not 0. And replacing y by minus y if necessary, we can assume that phi k of y is positive, and this contradicts the definition of M, right? Because now the it contradicts the minimality. Let me write it here. In the definition of M, because now this vector y is a witness that the m plus 1 tuple consisting of phi 1 up to phi m along with phi k doesn't satisfy statement 1. And so this gives us a contradiction. We chose M, sorry, I said minimality, but I meant maximality. We chose M to be the largest integer with this property. Okay, so we've proved the claim. And now we continue the proof with two cases. So the first case is when R is bigger than M plus 1. So, or in other words, M is less than or equal to R minus 2. So what we can now do is remove the last element from this R tuple. So I replace phi 1 up to phi R with phi 1 up to phi R minus 1. And this is an R minus 1 tuple. So the induction hypothesis should be valid for it. But if we use the fact that m is chosen as large as possible, one holds for this r minus 1 tuple. Now, this r minus 1 tuple is not an m tuple because of this assumption. And so so it can't serve as an example of an r minus 1 tuple for which 1 fails. So 1 holds, and r minus 1 is strictly smaller than r. So by the induction hypothesis, 2 also holds for phi1 up to phi r minus 1. That is, there are coefficients which I want to denote by rho i's. And these are positive coefficients. And they give us 0. Now, since the span of the phi's from 1 all the way up to r minus 1 are the entire dual space, this is from the claim and from the fact that m is less than r minus 1. There exists C1 up to CR minus 1 such that phi r is some Ci phi I. And now I want to prove 2 for phi1 up to phi r. So the coefficients are going to be lambda 1 up to lambda r. So I just choose lambda r some positive number arbitrarily. And now I choose lambda 1 up to lambda r minus 1, positive small enough so that something is confusing me here. No, I don't choose r, sorry. I'm sorry, I choose lambda r small. So that if I define, it's positive and small, so that if I define lambda I by the following formula, rho I minus lambda r Ci, then lambda I are positive for I goes from 1 to r minus 1. Okay, this formula, the rho I are positive numbers. We got them by induction. Ci are some numbers. We don't know much about them, some in real numbers. By continuity, we can take lambda r to be positive such that all of these numbers are still positive. And then we will get that the sum is 0. So I'll do the little computation and you'll see. So I opened up this sum and pulled out rho I phi I, that sum vanishes by the induction hypothesis. And what I'm left with from this sum, the lambda r I pull out, and I'm left with this sum ci phi I. Ci phi I, sum ci phi I from 1 to r minus 1 is phi r. So I got minus lambda r phi r plus lambda r phi r, total of 0. Let me write this more cleanly. Okay, and that completes the proof in case 1. Case 2, r is n plus 1, and let h be the kernel of phi r, and apply induction to h. So h has a smaller dimension than v. And for any x and h, if phi I of x is at least 0 for I going from 1 to r minus 1, then phi I of x equals 0 for I equals 1 to r. So in other words, 2 applied to h is valid because h has smaller dimension. 2 says that if I assume this, then I get this, not for all I from 1 to r, but from all I from 1 to r minus 1. But for I equals r, I also have this because x belongs to the kernel of phi r. And so this means that statement 1, statement 1 holds on the subspace H with these linear functionals. And that means that there are coefficients lambda 1 up to lambda r minus 1, all of them positive, such that the sum lambda I phi I goes from 1 to r minus 1, vanishes on H. So this is statement 2 for H and for this r minus 1 tuple. So now we have that M is r minus 1, and we know we're assuming statement 1. So that implies that there's a V in V such that phi r of V is negative and phi I of V are non-negative for I from 1 to r minus 1, and phi I of V is positive for at least one index I. So I don't want to spend too much time on this, but if you check what the induction says, this is what we get. And then using that, we see the following. So if we look at the sum of lambda I phi I applied to V, we get a strictly positive number. If we look at phi r applied to V, we get a strictly negative number. And therefore, we can choose a linear functional lambda r sorry, a linear scalar lambda r to make this sum equal to 0, right? This is a positive number. This is a negative number. We can just choose lambda r positive so that this plus lambda r times this becomes 0. And that what this implies is that this linear combination, sum lambda I phi I goes from 1 to r, vanishes both on H and on V. And since the span of this little v union H is everything, we get what we want. Okay, so this finishes the proof of the lemma. And let me complete the proof of the theorem and take us a few more minutes to complete the proof of the Voronoi theorem. So proof of the implication. In this direction in Voronoj's theorem, let me show you again what the theorem said. This implication. So I'm assuming now that L is critical, and I want to show you, I'm assuming that L is critical, and I want to show you that L is perfect and eutactic. And remember, we already had a theorem of Korkin and Zolotaryov that said that if L is critical, then it's perfect. So really what I need to show you now is that if L is critical, then it's eutactic. And I'm allowed to use the lemma. So we already showed, and this was theorem 0, that L is perfect, and we want to show that it's eutactic. And we apply lemma 5 to the linear forms minus trace union phi x in min L. So let's just look at lemma 5. So, but keep in mind that these are the linear forms phi1 up to phi r that we want to take. And so lemma 5 says that we can find linear functionals. Where is this? Statement 2, condition 2 of lemma 5 says that we can find positive scalars lambda I such that we have this identity. One of these phi i's now is minus trace. So moving minus trace to the other side and dividing by the corresponding scalar is going to give us exactly that the trace is the sum of the phi of the phi x's with positive coefficients. And so statement 2 here is exactly what we need with this choice of the phi i's. And so because we have the implication 1 implies 2, we actually need to verify 1. Okay, so 2 of lemma 5 implies L is eutactic, and so we need to check 1 of lemma 5. So we need to show that if, so the V that we're using is the space of symmetric matrices. We want to show that if the trace is non-negative and phi x of a, sorry, the trace is non-positive and phi x of a is non-negative for all x in the minimal set for L, then all of these things vanish. That's what condition 1 boils down to in the case of V being the space of symmetric matrices and with these choices of the linear functionals. And so to do this, let's choose a parameter, let's call it K. And I want to define A prime as being A minus K times the identity. Then the trace of A prime is the trace of A minus N times K. And for X, a minimal vector for L, phi X of A prime is phi X of A minus K times K times lambda 1 squared of L. So if you remember so if you plug in the identity into the definition of phi X of A, so again, so A prime is this quantity, and phi X is a linear functional. And so this is phi X applied to this minus K times phi X applied to the identity. What is phi X applied to the identity? Phi X applied to the identity is exactly the length of X in L. The length of X squared. The length of X in L squared is lambda 1 of L squared. And so the minimum of phi X of A prime is the same thing for A minus K times lambda 1 squared L. Let's choose now. I haven't chosen K yet. Now let's choose it. Let's choose K to make this minimum equal to 0. So K is non-negative, and this implies that the trace of A prime is less than the trace of A, which is non-positive. And now looking at statement B of our theorem, we get that A prime is equal to 0. And so this means that A is K times the identity, and I'll just continue the whole computation. Okay, so um, so basically, this is just calculations, and everything works out. So I don't want to spend too much time just going over this step by step, but you can check that all the steps work out fine. So maybe we'll take a 10-minute break, and if anything is not clear about this, I'll leave this on, and if anything is not clear about it, you can ask about it after the break. Okay, let's take 10 minutes. Okay, let's continue. Please, someone just make us indicate that you can hear me again.
Yes.
Okay,
We can
thank
hear
you.
you.
Okay, good. So what have we proved? Ooh, sorry, my laptop wants this.
That's Switzerland.
Okay. That is Switzerland. That's correct. Outside Zurich.
Where is it?
It's outside Zurich. I forget the names of those mountains. It's about 1 hour south of 1 hour
Yeah,
south
it's
of
around
Zurich,
Schwyz, I guess. Okay.
perhaps. Yeah. So where is the theorem? This is the theorem that we proved right here, Voronoi theorem. So Voronoi theorem is really nailing the local, the sort of the geometric properties of local maxima for this packing quantity that everyone cares about. It's a really very, it's a pair of very explicit conditions that are checkable, and you're going to see in your exercises that it's really checkable in a given dimension. You get some equations that you have to solve. It's not impossible to check. It doesn't seem impossible to check this condition. And so now we know what the local maxima are, and in order to find the global maxima, we just have to take the largest of the local maxima, the largest of the values of this function lambda 1 bar over all of these local maxima, and then we'll know the maximum. So that's kind of the strategy proposed by Voronoi in 1906. And to just make sure that this strategy makes sense, he had to prove the following theorem, which is what we're calling theorem 3 of Voronoi. And that is that this is really a finite algorithm. And so for each n, there are only finitely many local maxima to check. So for each n, there are finitely many critical lattices in xn bar up to similarity. Remember, this xn bar is our notation for the collection or the space of all lattices in dimension n. And in fact, we're going to prove a stronger statement. Voronoi proved that there are finitely many perfect perfect lattices in xn, and in particular, by theorem 2, finitely many critical lattices. So for this finiteness statement, you only need to work with perfect lattices. Okay, so this is the next theorem that we're going to prove. Remark, in 1977, I guess I should say the century because this is a classical topic. In 1977, Ash proved that there are only finitely many eutactic lattices in Xn, again up to similarity. So you could do this kind of algorithm in two different ways. You could first enumerate all the eutactic lattices, then you could strike out those which are not perfect and stay with all the eutactic and perfect lattices. Or you can reverse the order and first enumerate all the perfect lattices and then strike out all the ones which are not eutactic. And that would leave you with all the critical lattices by the previous theorem, by theorem 2. And then you just check the maximal value of lambda 1 bar and you will have the global maximum of lambda 1 bar. So that's the strategy. So let's prove theorem 3. So it's a proof by taking limits. And so this is not exactly Voronoi proof, but it's a proof sort of using the machinery that we've developed. So let's let L1, L2, etc. in X and bar be pairwise non-similar perfect lattices. So this is an argument by contradiction. So we take an infinite sequence of perfect lattices which are not similar. No two of them are similar. And let's rescale. So often one rescales the co-volume to be 1, but we're going to be rescaling so that the value of lambda 1 is 1. The shortest lattice vector is of length 1 for each j. Remember, the quantity that we care about is invariant by scaling. And so once we know lambda 1 and we know that we're perfect, we saw that when you're a perfect lattice, the value of the first n Minkowski successive minima are all equal to the first. In other words, the lattice has sufficiently many shortest vectors to span all of Rn. So as we saw, for each perfect lattice, the minimal vectors span Rn, and hence the first successive minima is equal to the second successive minima all the way up to the nth successive minimum. And we know that the product of the successive minima is comparable in size to the co-volume of a lattice by Minkowski's second theorem. Where this notation, again, comparable in size, means that the ratio of these quantities is bounded above and below by constants which depend on the dimension but don't depend on L. And we're interested in a fixed dimension. So we know that the co-volume now is bounded above, and this is always 1. I should have written that down. We rescaled everything so that lambda 1 is 1. All of these quantities are the same, so the product is also 1, and the co-volume is of comparable size to 1, which just means that for every one of these j, so there exists a positive constant such that for every one of these j's, the co-volume of Lj is bounded both above and below by 1 over c and c respectively. And so we had a compactness criterion for a sequence of lattices in X and bar, and we saw that if the shortest vector length was bounded below and the co-volume was bounded above and below, then this couldn't be a divergent sequence. So by a proposition from the previous lecture, This is like a compactness criterion. Lj does not diverge to infinity as j goes to infinity, i.e. has a convergent subsequence. And I'm just going to, as I always do, I'm just going to pass to this subsequence to assume that it converges. So passing to a subsequence without introducing a new notation, assume Lj converges to L infinity as j goes to infinity. Now, let's look at the balls of radius. I'm claiming now, the size of the collection of minimal vectors is bounded above. Independently of j. Okay? To see that, let's look at these minimal vectors and let's put balls of size radius 1/2 around them. So for each j. Okay, so these are balls of radius 1/2 centered at points of the lattice, and the shortest vector in the lattice has length 1 exactly, and so the distance between two different lattice points is at least 1, so these balls are disjoint. The balls are disjoint and they're contained in the ball around the origin of radius 3/2, right? Because again, all of these x's are minimal vectors, so they have length 1, and the ball around them is of radius 1/2, and so this ball is contained in a ball of radius 3/2 around the origin. So by volume considerations, the volume of this union of balls is less than the volume of this ball. The volumes of this union of balls is 1/2 to the n times a constant, and this is 3/2 to the n times a constant. And so the number, I guess I should decide whether I'm using what I'm using for which notation I'm using for cardinality. I don't remember what I used in the past. So the number is less than 3 to the n. Okay? So passing to a subsequence, I can assume that the number of elements which are of minimal length in Lj is always the same. It's some number m, and it's independent of j. And let's write Lj as gj times z to the n, where gj converges to g infinity, L infinity is g infinity times z to the n. So this was one of the ways we saw that we can understand convergence in the space of lattices in this way. So a sequence converges if it can be represented by elements g and glnr, which also converge in glnr. And so this is the choice that we've just made. And let's look at min j, which is gj inverse min Lj. This is some subset of z to the n. And this is the set of vectors in z to the n, which become the minimizers for the lattice Lj. In other words, if you apply gj to z to the n. You get Lj. If you apply Gj to this set, you get the minimizer, the vectors of minimal length in Lj. Okay? So this is a sequence of matrices which converges to G infinity, to the inverse of G infinity. And the vectors here all have length 1. So the vectors in this collection all have vectors of bounded length. And so for large enough J, vectors in min J have length at most 2 times the operator norm of G infinity inverse, right? Because the GJs tend to G infinity, the GJ inverses tend to G infinity inverse. So for large enough J, the operator norm of GJ infinity is less than this number. And we're taking a vector of length 1 and we're applying a matrix of this operator norm. So we have vectors of this length. And so all of the sets min J that I'm discussing here, they're all contained in Zn, and they're all contained in vectors of this length, and they all have the same cardinality. So there are only finitely many possibilities for them. So passing it to a subsequence again, can assume that min J is let's call it M0 or min 0, or let's just call it min, is the same for all J. And so to get a contradiction, we're going to show that if we have two elements of the sequence, which again, to make the notation easier, I'm just going to call L1 and L2 and then G1 and G2. So we have L1 equals G1Z and L2 equals G2 Zn, where lambda 1 of L1 equals lambda 1 of L2 equals 1, L1, L2, perfect, min L1 equals G1, this set min, and the same for G2, for L2. If we have this, then L1 and L2 are similar. Okay, so passing to all of these subsequences, we arrived at a situation where we have two lattices from this sequence that we started with, which was an infinite sequence, and they're both perfect lattices. The size of the collection of minimizers is the same, and the matrices which give them which map Zn to these lattices, if you pull back the minimal vectors under both of these, you get the same set min. And I'm claiming that this can only happen if L1 and L2 are similar, and this will give us the contradiction that we want. So let's take, to do this, let's take, so we want to show that they're both similar. So to see this.
In this step, this is not true if L1 and L2 are not perfect. If you would just, if you would, or say you have some.
Yeah. Right, here I'm going to use the fact that L1 and L2 are perfect. It's not true, you can find two lattices which have the same minimizers. I mean,
Yeah.
they're not exactly the same minimizers. They come from the same elements of, just think of kind of a lattice in general position in R2. It's got two,
Yeah, sure.
yeah,
And if you assume that the consecutive minima agree, then they have to be.
the successive minima agree. Even then, you in high dimension, you have enough flexibility to
Okay.
wiggle the geometry. You can't. The point is, you can't wiggle the geometry if you're perfect.
Yeah.
That's what's going to come out of this calculation. So so to see this, let's let x be an element in Zn of this set that I called min, and let's let so x is the preimage under G1 of some vector y in the minimizer set of L1. And so here's a little calculation. The length of y is 1. Y is G1 applied to x. Um, and so we get this, let's call this A1, where A1 is A of G1. Similarly, notice that this fact here, I've expressed this without reference to the minimizer set of L1. It's only with respect to the set min, which is the same set for L1 and L2. So similarly, 1 is A2, x comma x, where A2 is A of G2. Just repeat the same computation. So this implies that for all x in min, the difference A1 minus A2 applied to x, this inner product, which is a linear functional on with respect to the a's, has to be 0. And so let's carry out a calculation. So this is the same as A1 minus A2. And here I will go back to using, from now on, I'm only going to be using the perfectness of A1, of L1. And so I'm rewriting this in terms of a condition involving the minimizing vectors of L1. So the y's are the minimizing vectors of L1, and they're connected to the x's by G1 inverse. So I have this. And this is true for any y in in the minimizing set of L1. So since L1 is perfect, maybe I'll make one more, I'm sorry, I'll make one more line here. This is also the same as, I want to be left with a y here and a y here. And here I'm going to have G1 inverse transpose, E1 minus E2, G1 inverse. Okay, so I moved the G1 inverse to the other side and it became a G1 inverse transpose. And this is true for all minimizers of L1, and L1 is perfect. Since L1 is perfect, this can only happen if this is 0. But this implies that A1 minus A2 is 0 because we're conjugating by an invertible matrix. And this implies that G1 transpose G1 equals G2 transpose G2. And this implies that, so this is a computation similar to what I did at the very beginning of today's lecture. I'm moving the the G1 over to the other side. If my And so this means that this matrix is the inverse of this matrix. So I can move this matrix to the other side, and I get that G2, G1 inverse, G1 minus transpose, G2 transpose is also the identity, which means that G2, G1 inverse is orthogonal, which means that there exists an element of the orthogonal group such that G2 is O times G1, which means that L2 and L1 are similar. So this is a contradiction, and this proves our.
Barak?
Yeah.
Can you scroll up a bit?
How far?
Yes. So here.
Yeah.
So you said A1. I think A1x is not equal to G1 transpose G1x of x. Like there's missing a one there. No.
I don't understand where.
So G1 transpose G1x with x is equal to x with x plus A1x with x. No, that's how we defined A, right?
Oh, the
G
identity.
transpose G.
The identity is missing. Oh, thank you. It's not. Yeah. Let's just. I'm sorry. Just ignore the fact that these are A of G1s. You're right.
Oh, these aren't. Okay.
I'm sorry. These are just the G1 transposes. Sorry. You're right.
Okay. Right. Thanks.
And similarly here. Thank you. Okay. Yeah. Okay, so this proves the theorem of Voronoi. And so this sort of concludes this. So this is like an interesting story. This is like a bit of a dead end in 19th century, early 20th century mathematics. Everyone realized that this problem of finding the densest lattice packing was an important problem. And Voronoi and Korkin Zolotarev came up with this very nice local theory that completely described the structure of these maximizers. So you might ask yourself, well, what's wrong with this? Why is this a dead end? And so now the algorithm becomes, let's just search for this. This is a finite Okay, this is a finite collection. Let's just go over this finite collection, find the maximizers inside this finite collection, check all of them and find our maximum. And that's the end of the story. Now, there's two issues with it. One of these was solved and the other is a real issue. So the first issue is that the proof that I gave of this theorem, where did it go? Theorem 3 didn't give us an explicit bound or an algorithm for finding this finite collection of perfect lattices. Okay, and Voronoj's proof was explicit. In fact, gave explicit bounds. So this only looks like an issue, but if you had used a better proof than the proof that I gave, you would have had a completely explicit bound on the number of these perfect lattices. And moreover, this theorem doesn't tell you how to find all of these perfect lattices. It just tells you there are finitely many. And Voronoi actually gave an algorithm for finding all of them. So there actually is an algorithm for finding all the perfect lattices. And so what could be the catch here? It looks like it's just sort of solves the issue. The catch is just that the number of perfect lattices is large. And the algorithm is maybe not as efficient as you would like it to be. So here's a table. I made a table of what's known about this enumeration problem. So in each dimension, I'm giving you the known number of the critical lattices, which is what we're after, and the perfect lattices, which is sort of the way the algorithm finds them, and the eutactic lattices. So it starts off very nicely. So in dimensions 2 up to 5, the number of perfect lattices is the same as the number of critical lattices, and there are only 3 of them in dimension 5. And all of these were found by Korkin and Zolotarev in the middle of the 19th century. In Voronoi realized, apparently, according to the history, when he arrived at dimension 6, he realized, actually maybe 5 was not done by, I don't remember. I told you this last time, but now I don't remember whether this case was done by Korkin Zolotarev or by Lichfeld. But in any case, Voronoi realized in the beginning of the 20th century that there are lattices which are perfect and not critical. And then he came up with his complete characterization that you need to also add eutactic and this enumeration, but the numbers were still, so this fact that 7 is bigger than 6 is telling you that there is a perfect non-eutactic lattice in dimension 6. And Voronoi realized this, and the problem was sort of completed by hand in dimensions 6 and 7 after Voronoi died. And then in dimension 8, just there were just a lot of perfect lattices. And so finding them became time consuming. So this is now a computer assisted proof. It's a rigorous computer assisted proof. 10,000 and so perfect lattices, 2,400 of them are critical. And this is one way to know the maximal packing density in dimension 8. When you go to dimension 9, you continue with the computer search and you see at least 20 million perfect lattices. And this computation, as I said, it can be done, but there's an algorithm, but this is a computation that took several months to do. And in these kinds of computations, there are 2 types of computations. One of them sort of gives you the list and gives you the correct answer. And the second one, as we saw when we were discussing Hales, is kind of a verifier. It proves that the output of the first computer program was correct. So that takes even longer. So this took approximately 6 months. It could be that the number is actually much larger. And this is only the algorithm which tells us what the perfect lattices are, but it doesn't tell us rigorously that this is all correct. So that would take several years to run in dimension 9, and that hasn't been done. And therefore, the problem, it just is not feasible for a computer. It just becomes too big to do all these computations. And you see that it's sort of, it's an exponential problem, and you see that it's exploding very rapidly at the transition between dimension 7, it's manageable by hand. Dimension 8 is the only dimension where it's manageable by computer. It's maybe conceivable that dimension 9 could be done by a computer within our lifetimes, but we can't conceive of a computer capable of doing even dimension 10 with this kind of an algorithm. Now, there are upper and lower bounds for the number of perfect lattices. And this is what they look like. So it's at least exponential, and probably the upper bound is close to the truth. There are conjectures to the effect that the upper bound is close to the truth. So presumably the number of perfect lattices is super exponential in the dimension. And by dimension 9, it's quite large, and 10 and higher, it's unmanageable. And regarding eutactic lattices, there have also been some computations, and there is no enumeration of eutactic. We know it's a finite number, as I said. There is no enumeration past dimension 6, but there has been some kind of computer work to try and check whether we expect there to be more eutactic lattices than perfect lattices. That's certainly true in low dimensions, and it also seems to be true in higher dimensions, at least in dimensions approximately 8, 9, or 10. there are more eutactic lattices than there are perfect lattices. Okay, so this is sort of the outcome of this failed attempt to understand the maximizer for the packing density. Okay, any questions about this discussion?
This in the first column, you have the critical ones. These are not maximizers of the packing density, or are they? These are local maxima.
Right, and one of them is the maximizer. Just because,
one of them is the maximizer, but the
right. So in this,
how many, or do we know how many?
You're asking whether you're asking whether they're ties?
Yes.
I don't believe there are ties, but I'm not sure. I think there are no ties. I think I gave you the list of the maximizers in a previous lecture, and I think there's a unique maximizer in all of these dimensions.
Okay.
It's in the notes.
Yeah.
But conceptually, I mean, kind of conceptually, there could be ties, and there's really no reason for these two numbers to actually come out to be the same. It would seem somewhat magical, but maybe as the numbers grow, why not?
Okay.
Okay. Yeah. So that's what I wanted to say about this problem. Let's see. We have about 8 minutes. So let me tell you where we're headed next, and then let me somehow give just a tiny bit of additional kind of philosophical remarks about the proof that's been these proofs that have been occupying us for these past 2 lectures. So where are we headed next? So as I said, this is a wide open problem to figure out the optimal lattice packing density in high dimensions. There's one exception, which is dimension 24, where you have this magical Leech lattice, which not only is known to be the maximizer, but it's also known to be the maximizer for the general sphere packing problem, not just by lattice packings. So given that we can't solve this problem, what we can next try to do is put a measure on the space of lattices and try to figure out what happens for a typical point with respect to measure. So we're going to be thinking, this is like some of you may know the probabilistic method in combinatorics. So we're going to be putting a probability measure on lattices in dimension n. To be more precise, it'll be lattices of covolume 1 in dimension n. There's going to be a nice probability measure on them. And then we're going to ask, what's the probability that a given lattice has packing density bigger than some constant c? And if we can prove that that probability is high, is positive, that means that such a lattice exists without ever being able to exhibit one concretely, explicitly. So if this strategy that we're now looking at, if this strategy that's sort of summarized in this table were to be successful, not only would we know, you can sort of imagine that you were extremely lucky and that this kind of a pattern persisted. In every dimension, there was just 1 or 2 perfect lattices or something like that. Then you would also get that these perfect lattices probably have a very nice description, and you have an explicit solution to the perfect lattice problem in all dimensions. That turns out not to be the case. And so now we get 2 different kinds of problems. One is, what's the maximal lattice packing density? And the other is, what is a lattice exhibiting the maximal packing density? Now, we don't know anything about these 2 questions, so we can weaken both of the questions, and we can ask, what's a lower bound on the maximal packing density? To get this lower bound, we just need to show that some positive probability of lattices have a fixed lower bound on the packing density, and that's one direction that we're going to take. And the other direction is, can you explicitly construct lattices whose packing density comes close to the bounds that you have? And that's, again, an open question. So we're going to be showing you probabilistic proofs of existence of lattices which have bounds, lower bounds, on their packing density, but we don't have explicit constructions of these lattices. Okay, so that's happening starting next week. So now I just want to give just a general little diagram that summarizes one of the ideas that came up here. One of the confusing things about what we just discussed is that we discussed symmetric matrices, we discussed ellipsoids, we discussed quadratic forms, and we're discussing lattices. So let me just summarize why this all came up. So if your ball is, if we use the Euclidean norm and your ball is the set of x's which satisfy this, and we're using the inner product now, then the image of this ball by B, so this would be y such that right, if I apply an element G to X, I get an element Y, and it satisfies this formula, which is the same as saying that Y satisfies this kind of a formula for A being G inverse transpose G inverse. And so we're getting a connection between, so this is a general ellipsoid, and this is a general symmetric matrix. So we're getting a connection between ellipsoids and symmetric matrices via these kinds of functions, which are called quadratic forms, positive definite quadratic forms. And sort of in terms of groups, I just want to write this little diagram down. And so we have bijections between the following objects. So norms associated with positive definite quadratic forms, just a way of saying inner product on Rn. These are in bijection with ellipsoids. These are in bijection with positive definite symmetric matrices. These are in bijection with GLNR over ONR. The left cosets of the orthogonal group in the space of invertible matrices. And this is the map that we sort of used over and over again. So I'm just stressing here that we again see a quotient of GLNR by some group, but this time in terms of our conventions, we're quotienting by a group appearing on the left. Okay, when we construct a space of lattices, we're going to be quotienting GLNR by a group acting on the right, which is GLNZ. Okay, and so you can think about this in several different ways, but it's sort of important to distinguish the action on the left from the action on the right. The multiplication on the left by orthogonal matrices doesn't change. So somehow the space, I'll just write it down and we'll continue with this next time. The space of interest to us will be basically S ln R over S ln Z quotient from the right by S ln Z, quotient on the left by O and R. These are basically similarity classes of lattices of covolume 1. Okay, so this is a good time to stop. So I'll see you all next week, and then we'll be constructing this probability measure on the space of lattices.
Thanks. Bye-bye.
תודה, להתראות.
Bye. להתראות.
Thank you.
Thank you.
Thank you.